we're group 5.
These are our names.
Reading stress in the muscle.
We're finishing our biocompatibility tests to see if the algae grew as much with the tubes or the materials that we're using that weren't provided to us as they did without anything. We also did the experiments with the biocompatibility and we got the results that everything is biocompatible.
Our sensor and LED are housed in plastic test tubes placed strategically within the bucket. The sensor is mounted on the bucket side and the LED is positioned centrally to evenly illuminate the algae. We capture raw data from 4 channels, red, green, blue, and clear. To calibrate these readings, we conducted experiments at known algae concentrations and various LED brightness levels. We discovered that the blue and clear channels provided the most reliable data as algae absorb UV and near UV blue light effectively. Using the formula OD equals log 10 times RO divided by R, where RO is clear water and R is the current reading, we established linear regression models for algae concentration based on OD values. Specifically for the blue channel, we derived that concentration is equal to 486,850.81 times ODB minus 2,589.31, and for the clear channel, concentration is equal to 518,613.30 times ODC minus 461.35. Our test revealed that 50% LED brightness gave the best results, offering smooth, reliable data. In contrast, lower brightness caused inconsistent readings and higher brightness levels introduced significant noise. Similarly, white LEDs added considerable noise, making the data difficult to linearize, so we decided to turn the white LED off during measurement periods. To further enhance accuracy, we implemented a Heidemann filter, incorporating an algae growth model from lab data. This improved our system's reliability by placing more trust in model growth rather than noisy sensor data. In practical use, the sensor performed slightly worse due to water transparency variations, oxygen bubbles from algae mixing, and muddy water introduced from another system. Nevertheless, we still achieved a good approximation of algae concentration. Looking forward, improvements could include controlling mixing during measurements and better calibrating for transparency variations.
We decided to do our experiment with one muscle, and the chosen one is Gary.
Now the system's overnight, so we can test out to see if we get the values and to see if the muscles survive.
For the feeding rate calculation, the optimal concentration for the mussel bucket is 1,200 cells per milliliter, with the filtration rate of 4.45 liters per hour per mussel. With this, we calculate the amount of cells that each mussel eats per hour. With that and the growth rate, we calculate the ideal concentration in the algae bucket, so that the amount of algae cells we send to the mussels is the same as the amount of algae growing, keeping the concentration constant. With that, and we calculate how much we need to send from the algae bucket to the mussels per hour. The concentration in the algae bucket is 35,132 cells per milliliter, and the feeding rate is 26.32 milliliters an hour. We decided on only using one mussel in our system, so the calibration in the algae bucket follows the OD calibration.
By manually tuning the parameters partial to 0.8, integral to 0.03, and derivative to 0.2 for the PID temperature controller, we were able to successfully implement a code to maintain the water temperature in the mussel bucket to around 17 degrees.
For the innovation part, we designed our system using 2 Arduino server solenoid 3D printed valves instead of 2 submersible pumps, which shows a smarter system architecture by reducing components, which proved to be more energy efficient. Moreover, it demonstrates advanced control algorithms. Additionally, we used 2 recycled thermo boxes that we sourced from the recycling station to use as thermal isolation and keep the temperature of the system lower, reducing the activation of the cooler system, improving the energy efficiency, which was proved by the 2 experiments. From an insulation test, we were able to observe that the insulated system maintains the water temperature more effectively than without insulation. We also noted that the insulated system was more stable and maintained the temperature in a linear way, making the cooling of the system more predictable.
We use a web interface to remotely monitor and control a few parameters in the system. We created a feed for each of the parameters we wanted to show, such as temperature, algae concentration, route, and valve status, and we set it up in a way that we can change the parameters of route in a system in real time. We can decide whether we want to feed the algae in real time or whether we want to close the system through the MQTT messages.
We were able to make a system which is controlled by the web server. It's energy efficient as we only use one pump, and it's innovative as it uses a 2-way valve system.